Can you guys hear me well? Okay, let me stop from here.
We can hear you.
Yes.
Nice. So just for info today, I'm gonna try to like do the presentation on an iPad because some of the students told me it's easier to annotate on the screen, and that might be easier for you for understanding. And we're gonna just experiment with some different software for taking notes and collaborating with each other, right? So the lecture officially starts in 1 minute, but let's just wait a little bit longer for everybody to join. So far, I see that the majority are in the Telegram group, but technically we have 22 students in this course. So there are still some students who are not in the Telegram channel. Participants. Okay. Do you guys get any notifications when I put the Zoom link on Moodle?
On Moodle, no.
Yes.
Okay,
We
some
received
students go.
emails.
You received an email. Okay, so you received an email about it.
I don't. I mean, seemingly not all of us.
Okay. Da, 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 da.
Oh yeah, got it.
You got it.
Yeah.
Okay, maybe I should just put it here also. Zoom link. And just make sure everybody can attend. Nice. Okay. So now they can even see it on the right screen of the Moodle. Yeah. Can you guys hear the washing machine in the background?
No,
No, that's awesome. Wow. It's super
it's
loud.
not. No, I mean, yeah, it's not so obvious.
It's not so obvious. Nice. It still has like 8 minutes left, so we're gonna suffer with that one a little bit. So we have 13 people joined. I'm just gonna quickly go through the participants list, and you guys tell me who is here and who's not. Okay. So we have Gorobevskaya. So Nadezhda. No, not here. So this person was added as a guest to the course, so just maybe somebody who would not grade it. Next is Artyom Bakhanov. Are you here? Artyom. Yet he's not here. But I saw him, I think, on the group, so probably will join soon. Next is Anna.
If it's me, I'm here.
Nice, so you're here. Lev, you're here. I think I just saw you.
Yeah, I'm here. Hello.
Hello, nice. Maxime.
I'm here.
Nice. Ahmed Hamdan, you're here.
Yep.
Utkarsh Kalra. Utkarsh, I see that he's not here. And he is a student. He's a graded student. He's gonna fail this course. Then we have Kamil. Kamaliev.
I'm here.
Nice. Hello. Then we have Farhoud. I think Farhoud has had some problems last week, and maybe he's still having the same problems. Then we have Yusuf Musbah. Are you here?
Yes, I'm here.
Nice. Ozyoma. Yes. Ozyoma, let's check if she's at least in the Telegram group.
Yes, I'm here, and I joined just this evening on Telegram.
Ah, nice. Good. Ozzy. It's Ozzy. Okay, cool. And we have Dimitri.
Hello.
Hello. Mauricio. He just texted me, so he should be here. Like I sent him a message. Mauricio, are you here? Nice. Mauricio is here. Yaroslav. We don't have a Yaroslav here. Yaroslav, yet. Let's check if he's in the group. Yaroslav, yes, he is in the group, so he just didn't join yet. Yaroslav. Rufina,
Yes, I'm here.
cool. Maxim Sokolov. Maxim Sokolov is not here. Okay. Maxim, nice. Oh, I think he's here. No, that's another Maxim. That's Maxim Evgarov. Okay. Then we have another Lev. So Lev Svalov.
Lev Svalov was before. I'm Lev Chudinov. We're both here.
Okay, so you guys are both here. Nice. Artur. There's no Artur. Artur. Nope. Let's check if he has at least the Telegram channel, and he's not here. Does anybody know Artur Tajiddinov? Tajiddinov. Okay, Artur Tajiddinov. Nobody knows him? Nope, nobody knows him. Okay. Viktor Vanishkov is also another guest. Oh, I remember these guys. So these are like the students who already graduated, but they wanted to. Yeah, okay, I remember those two. Then we have Hussein Yunus. Last time accessed the course 19 days ago.
Yeah, I'm here.
Nice. And we have Ilmir Ibragimov. Ilmir Ibragimov? Nope, not here. Yeah, these 4 students, I think they're just. Oh, that's okay. If they can't join, they can't join. So again, if you guys can see some of your fellow students who are enrolled in this course but still did not join, please send it to them. I think by now everybody should at least have access to the Zoom meeting and to the Telegram channel. They're all in the Moodle, so maybe they would get it someday. Nice. So just to make sure, the majority of you guys already took the course with me of Introduction to Computer Vision, right? Is there somebody who did not?
Yes.
Okay, so there are some students who did not take the course of Introduction.
I'm sorry to interrupt, but you forgot me.
Khalas, Ruslan. Ruslan?
Yep.
Oh, I did not see you. Are you sure you're enrolled?
Yeah, I'm pretty sure I'm enrolled.
Ruslan. Niet? Nope, I don't see you on the list.
Hey, give me a sec, I'll send you something on Telegram.
Okay. Are you enrolled like officially or just like a free listener?
Oh, I enrolled officially.
Officially? Well, I think the university just forgot to add you. Can you see the course?
In progress now.
Oh, weird. I don't have you on the list. Ruslan. Okay. Ruslan. That's gonna be weird because like this you cannot get grades, right? Can you at least see the course on Moodle?
Yeah, I see it on my university. Yeah,
On
because
Moodle,
I
can you see
applied
it?
to But on Moodle, I cannot see it for some reason.
That's why I cannot see you. Can you send me your email? Just please confirm with the education department that everything went correctly, and just send me your email. I will add you manually.
How can I confirm it? It's on my university website. I'm enrolled.
Just like go to the education department or like the people who are working on Moodle, and just tell them what is wrong, right? Just understand with them what's happening, usually they just add the students manually, so these problems can happen anytime, right?
Окей, ладно.
So just send me your Innopolis email and I'll add you manually right now. Anyone else who does not have access to Moodle? Copy and tech student, you're graded, right? Nice. Now can you see it? Just like press refresh and see. Ruslan, I can see you now.
I'm there. Thank you.
Nice. So just to confirm, everybody now has access to Moodle, everybody has access to Telegram, and everybody has access to, or at least the majority of you have taken the course of Introduction to Computer Vision, right? Just to confirm, Judicator, who just joined right now, who are you exactly? Like the name, so I know. Judicator. Let's. Okay, so now Artem also joined. That's nice. Let me just text him. Anyway, I think let's just get started now. So he just replied. And Yaroslav is also here. Okay, good. So just so you guys would know or would to have some expectation, this course is not going to be like the Introduction to Computer Vision course. This one is going to be like an elective focused on mainly advances in computer vision and focused mainly on research, right? So this course is just going to be me sharing the same experience that Professor Khan has given me in my first year and my second year experience. And basically, he was just mentoring me in, well, helping me in understanding how to do research, reading lots of papers, guiding me, and helping me with the writing. And I think that was a very, very useful experience because, well, he listened a lot and he spoke a lot, and that was very useful for us to understand. And certainly my life has completely changed after that. So that's what I'm trying to give you guys through this course, to allow you to get access to like some mentoring on computer vision, and of course, getting some knowledge about advances in computer vision. Before we like start the first lecture, and maybe let me just open my camera so that you guys could see me. Can you guys see me now? I don't see myself.
Yep.
Okay, you guys can see. Nice. So yeah, so I'm gonna share the screen, and hopefully share screen works well on this one. Computer vision and deep learning. Present. Standard. Nice. Share screen. Nicely done. For some reason, you cannot see my image anymore. Okay, now you can see my video. That's nice. And now you cannot. Wow, very weird. So yeah, so the course title is Computer Vision and Deep Learning. So we're gonna focus mainly on the computer vision part, but we will have some parts on deep learning, mainly the parts on natural language processing and attention. So if you guys remember, maybe during the lecture or first lecture of object detection, we saw the different architectures, and one of you guys just told me that now we have a new model that is super cool using attention, and it is the current state of the art in object detection and image classification too. So this is why we're gonna, before studying this new model, we're gonna have to spend a couple of times or a couple of hours studying attention in natural language processing setting, right? So this is the deep learning part. whereas the what is it called? The computer vision part is going to be very similar to the previous what we have seen before. So we're going to speak about image classification, but in this case, we're going to speak about every single architecture of image classification that has won the, for example, the ImageNet. What is it called? Yeah, the ImageNet challenge. And then we will have a cool lab where we will program our own image classifiers and perform some transfer learning. Hopefully through this lab, we will get some knowledge about transfer learning, what are the tips and how to do it efficiently. This is going to be the introduction because I did not really know who is the target audience of this course. So I just wanted to make sure that we have a solid basis or basics, yeah, that we can all start from, especially since we have lots of students who really did not take the introduction to computer vision part or who have not taken any course in the university in a long time. So they're still new to that. First, let's start with a self-introduction. So my name is Bikush Imad. I'm an Algerian, let's say, researcher. I studied my bachelor's in computer science in Algeria. Then I did my master's in data science in Innopolis, where I met the majority of you guys. And currently, I'm doing my PhD in artificial intelligence in Sorbonne University, which you can guys see the picture on the right. It's very beautiful. And my industrial experience can be summarized in the following. So I started working with a couple of Innopolis research labs, namely the machine learning knowledge representation lab. And then I went to industrial artificial intelligence lab. Yeah, that's the name. So industrial artificial intelligence center. Yeah. And from there, I started working with Provectus. So Provectus was a very cool experience for me and still is. So I worked on lots of computer vision models. I worked on image interpretability, worked on domain adaptation and domain drift detection for images and for tabular data and for text. And yeah, and then from there, we just completely changed the field and started working only on object detection models, but on the edge, right? So object detection models that are not going to be deployed on the cloud, but are mainly going to be deployed on edge devices, well, such as like nano devices provided by Amazon and other types of smaller GPUs. Nothing like mobile devices, but more like industrial GPUs, but are very small scale. You can find thousands of them, very cheap ones, and usually they are put in like associated with a certain camera or something like that. And they just do the processing locally because that data is very sensitive and should not be sent through the internet. So that was a very cool experience where I just learned a little bit about AWS and all of the services that it provides and how can we put object detection in an industrial setting. After that, I joined Pepsi as a data scientist, and currently this is what I'm doing, right? So this is what I'm working. It's pretty interesting, especially since we are like training thousands of models that are spanning, different continents. So majority of them are in North America, but some of them are in Canada, in Europe, just a few in Russia. So we don't work a lot with the Russian data sets, but yeah, it's pretty interesting. My research interests are mainly computer vision. So what we are studying right now, domain adaptation, which is a field or a subfield of transfer learning that I'm sure some of you guys have at least heard of before. Domain adaptation aims at bridging the gap between two different data sets. Usually you have one data set which contains lots and lots of data and is pretty much useful for training a full computer vision model. Whereas another data set just does not have enough data to train. So, but they are very similar to each other in terms of classes, or they share some classes, or they are completely the same classes, but there are some visual differences. So the goal is basically to close this domain gap and improve the results of the model on this small data set. The final part is knowledge graphs, and knowledge graphs are just a way of storing data. So let's see if what they said is correct, and using iPad is pretty useful. So knowledge graphs are the following, right? So for example, you take the Mona Lisa painting. So let's say this is Mona Lisa, right? So this is one node in our knowledge graph. It's connected to different other nodes. For example, it's connected to the node called Italy. It's connected to a node called the Louvre Museum. So this is the museum where you can find the Mona Lisa. Louvre Museum is connected to Paris because it's here. It's connected to Leonardo da Vinci. My writing is horrible, but I hope you guys get the idea. So it's connected to all of these different things. For example, we have other information about it, such as the date of creation, let's say 1960s. For some reason, I have no idea when it was built, and other different notions connected with each other. And here you will have like a graph that combines all of the data that we have. So for example, all of the information that we have about the Mona Lisa, we just create them together and link them together. Usually these connections either have no meaning, so they're just a connection between two different objects or two different nodes, or in some cases they have like a meaning. So each one has located in, stored at, is patient of, and so on and so forth, right? So this is what knowledge graphs are. It's a very convenient way of storing information. And the goal of my thesis currently in Paris is to combine both knowledge graphs with object detection models in order to improve the results of object detectors on specific data sets. And so basically it's just performing domain adaptation for object detection by using or by incorporating knowledge graphs. So this is like the theme of my research. If you guys want to contact me, usually I prefer being contacted through Telegram. You could use my email, but I really don't check it that much. So that's not going to be very helpful. So just stick with Telegram. I reply pretty fast. And this is the link to our Telegram group. So the grading criteria, I still have not really made it. We're going to be discussing it today. And from what I've learned in the last experience of teaching in the teaching of Introduction to Computer Vision, I saw that midterms and final exams were not very useful. Many students really said that they didn't understand the questions, and this is why they couldn't really answer correctly. So I'm going to start incorporating more. Let's try. Yep. So we're going to start having more oral exams in both versions. So oral exams will be just like the same thing as the midterm, the same content as the final exam, but this time you get me to we just have a small conversation. I can check your progress and understanding of the content. Sorry. And this will help to give you guys better grades and give me a better understanding of what you guys know and what you guys don't know, especially since we don't have a lot of students. So this is something very common in elective courses or even in master courses where you don't have lots of students, as we did in the core course. Quizzes, I'm still also not sure if we should have lots of quizzes. For now, we're going to keep 3 quizzes, and anything extra will be disregarded. Mini projects, again, we will have 3 homeworks. So the first homework will be on image classification plus interpretation. Second homework will be on object detection. And the third homework, we will see the topic depending on the courses or the content that we will see. The final project in this case is not going to be 15%, but it's going to have 30% of the grade. And for this case, we're not going to have any of these. We're going to have a research paper published, right? So during this course, I think we have the following schedule. Let me just share the schedule with you guys and explain to you what we will do in every single one of those weeks. Victoria. There it is, computer vision and deep learning. Let's put it here. Okay. No, 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 no. Yep. Nope. Let me try to find
May I ask
Telegram.
you one thing?
Yes, of course. Yeah, go ahead.
Just about the idea, why is final project is even a thing? Like, how? I mean, why we have this on course?
Why do we have the course? Why do we have the final project? Is that what you said? Can you please like repeat the question, maybe?
Yeah, why? I mean, what is the motivation behind the final project as a thing in the
Why
course?
do we have the final project? So the goal of having this final project is basically the whole goal of the course. So the goal of the course is to give you guys some experience with research, to allow you guys to publish research papers, and to learn the structure of building a research paper. So for example, from now on, it's not going to be very unclear for you. So we have the introduction. In the introduction, we should have like the following paragraphs. Let's say we first have the context paragraph, the problem definition, the current state of the art or current solution, your solution, the contribution or why is your solution very useful, where is your solution located, for example, in the tree in here. And then you will have a final paragraph that just summarizes the rest of the paper. Related works. So basically, this is what we're going to do. We're going to work together in order to build a structure of a research paper that you guys can easily follow in the following years. And hopefully that would allow you to work or get better PhD or master's options. Does that answer your question?
Not really, because we like the majority of people here is fourth grade,
Yeah.
fourth course, and they already have we already have like the thesis, so we anyway wanna know what is the structure of the paper should be.
That's true. That's true. So according to what Professor Khan told me about the course, or what he wanted to provide in this course, is to basically give the students the ability to do some research on computer vision field. So if you are already working on some project that is related to computer vision, very nice. You can just present that for me in the paper and in a paper form, and that's it. You have finished. If you're not working on that, then you would just basically start thinking about an idea and working on that in order to write some sort of a research paper. If the results are very good and significant, then you can just easily submit that and you have a published paper.
So we can just take the things from the thesis and present it to you if we...
Yeah, of course. If you are working on computer vision field, yes, go ahead.
Mhm.
Nice.
Yeah, thanks.
Thank you. So again, as I said, the goal of this course is to give you guys enough ability to research lots of research papers, right? So from here, from what I'm seeing, I'm sure you guys can also see it on the Telegram chat. So the first 4 weeks, we will have only 2 sessions, consecutive sessions, whereas the last 4 weeks, we will have 3 consecutive sessions. So in the first 4 weeks, we're not going to be doing lots of work on you guys. So mainly it's going to be just following some lectures and just following the lectures, following the labs and doing the homeworks. Whereas the last 4 weeks, every day, of course, we're going to have a lecture followed by a lab, and then we will follow it with students' presentations. And students' presentations, I will give you topics to basically research and present the topic every time. So usually we should have like 4 or 5 students presenting every session, and every student must present at least once. You will take some sort of research paper that you found interesting, and you will present it to the rest of us and explain it to us. So the goal is to basically make sure that everybody here can read research papers, know how to read research papers, and can easily understand them. And during this 1 hour or 1 hour and a half that is extra, what we will be doing is we will have discussions about your progress in the project. So it will be something like what you would do with your mentor, where you will just tell him what you're progressing with, what are the problems that are stopping you from progressing, and hopefully we will discuss that and get you some solution to get through that. Does that make sense? Do you guys start having a structure about the course so far?
Yeah.
You were
Nice.
talking about the labs. Maybe I misunderstood. We will have labs in in a standard manner, like 1.5 hour of lab, or just the homework as a lab?
No. You're gonna have the lab and the homework. Usually the homework is just the lab, but on a different data set, right? So when we do the homework, when we do the lab on image classification, I'll just ask you to go home and just repeat the lab with a different data set, with a different image size, play around with some of the hyperparameters, just to make sure that you guys understood very well the lab.
Okay, thanks.
Thank you. So overall, this is what's going to happen. What do you guys think about the paper presentations? Are you guys down for that? Do you find it useless, or do you find it interesting to motivate you guys to start looking at papers, especially from CVPR and things like that, and basically presenting them to us?
Do you mean just writing it or presenting it?
Can you go back and repeat, please?
Like, do you mean just writing a paper or presenting it?
No, in this case, basically, as we said, the first 4 weeks, we're not going to have any presentations, but the last 4 weeks, we will have an extra 1.5 hours during every single week. And in that extra 1.5 hours, we will do paper presentations. This is like something like you read a paper that you find interesting and you come present it to us. You come explain it to us, right?
Yeah, I understood.
Хорошо. So do you guys think this is a useful thing? Do you find it too much work? Is it too difficult for you guys to just search for a good paper on CVPR, for example, and read that paper? Is it a difficult task or a simple task for you?
I guess we can tell until we try.
Yeah, we can't tell until we try, but it's pretty
No, I
important.
can tell that it's like, for me, it's not going to be very interesting. Like I'm mostly interested in practical CV rather than research CV.
Okay, so you are more into practical applications. In that case, we can make like, can somebody tell me for those who have like, what are they called? Practical goals in mind. So they don't want to continue their masters. Basically, they want to stop in what is it called, in bachelor's and start working directly. Please just send me a message on Telegram and tell me what you guys want. And for that, we can make exceptions. For example, instead of presenting a paper, you could present to us different, for example, let's say object detection models, and you would compare them in a practical manner. For example, you just tell us, this one is pretty small, this one is pretty big, this one is very fast, this one is very slow, this one is like that, this one is like that. And then you just analyze where can this one be used, where can this one be used. So something that is very important is to understand where each model can be used. For example, you can't use YOLO v4 large model on a, for example, what is it called? On a mobile device, or you deploy it on like on a laptop or on the edge devices. So these are things where it's pretty impossible. It would be nice to get this comparison of these different models from not a theoretical and research point of view, but from a practical point of view. Does that interest you?
Yeah.
Nice. I'm speaking about the person who was like, who was against theory, but pro practice, right?
Yeah, that's me.
Nice. Do you like this comparison? Because this is something that I personally have done and spent a lot of time working on when I was doing the work on object detection for industrial applications. And these comparisons came out pretty useful.
Well, I mean, I certainly like it more than the papers. I would
Nice.
maybe like I don't know, I could think of another scenario. For example,
Yeah, go ahead.
what could it like detect? Well, I mean, just solving some practical task, and I don't know if that's already been done. Like maybe all of the CV applications have already been, I don't know, researched, and there's nothing else to do. So we only have to resort to comparisons. Is that the case? Maybe there's like, I wonder if there's a problem that is not solved yet. So we can actually like, and not just take two classifiers or whatever, two object detectors and compare them, but rather find one that just works.
If you, well, you can do whatever you want, like choose a topic, for example, image classification, object detection, whatever it is that you want to experiment with, and try to put, like, imagine a setting where it's an industrial setting. Be creative. Everything you want to do is doable. Whatever you can imagine, it's possible, right?
All right, we'll see where that goes.
Nice. So same thing for everybody else. If you are not pro research and you would rather, for example, just have some sort of a project instead of having a research paper, but have like some GitHub project that you can showcase to different interviewers during the interview process, that comes up pretty handy, especially if you are like going to have a technical interview. Usually you just show them your code, show them what you have done and stuff like that. And that's pretty impressive for the majority of interviews, and that would set you apart from other candidates.
So one more question. So we have two things, one paper that we need to write, and we need another paper that we need to read and present, or just
Yes.
some practical stuff. Okay, so we have two things that they're separate.
Yeah. So
Okay.
if you want to go with the theoretical part, so in that case, you're going to have to publish a paper. And if you're going to have to, you're going to want to do something like industrial work. In that case, you're going to want to find something that's interesting, present it to us, and then do your work on it. While you are writing, let's go back to the case of theory, while you are writing your paper, you're going to have to check out what is the different state of the art in that setting. And in order to do that, you're going to have to read lots of papers, take one of these lots of papers that you found interesting, and present it to us during one of those days, right?
So just to be clear, there are two possible options to choose.
Yes.
The first, it's to write the paper as a
Yes.
final project, and every week present the papers that you are reading while you're doing your paper, right? And the second,
1 week, only one time, not every week, just one
okay,
time you
one week,
present the
okay.
paper.
And
Yes.
the second option is to do the industrial project, like practical application of what we are studying.
Yes, exactly. Yep.
Okay, thank you.
You're welcome. So does everybody now at least have a better idea of what we are going to study?
So
how
it's
we
not
are
like not like we have a paper to write and a project to do. I'm
No.
still lost about.
Yes, you have one paper to write, and that's it.
And the project.
Okay. The project is the paper.
Okay.
So writing the paper, you're going to have to do lots of coding, you're going to have to do lots of experiments, and then you're going to have to showcase your results, right? Make sense?
Yes, thank you.
Хорошо. So the topics, or at least some of the topics that we will cover during this course, the first week or this day, we're going to speak about image classification, CNNs. If we have enough time and we progress fast enough, and I see that everybody is very familiar with CNNs, we will go through the interpretation lecture. In the interpretation lecture, we will speak about different manners. What is interpretations? What are the different ways of interpreting a model, and how to interpret specific types of models, right? So either how to interpret models in a white box manner. So basically you just dig deep into the model and try to interpret its results, or you just treat the model as a black box. You have no idea what model it is, or what model it is. Is it neural networks or or decision trees, you do not care. You treat the model as just a black box and you try to interpret its decisions. So this is what we will do in the interpretability lecture. And then we will go through the object detection and instance classification, instance segmentation again. I think the lecture will be very fast since you guys have already taken that, but the labs are going to be a bit more challenging in this case. Can somebody tell me what did you guys do in the labs with Karam, right? On these two topics, object detection / image segmentation, instance segmentation.
For object detection, we used YOLO as it's written on the slide, and that's it. And for what? For image classification and segmentation?
Image segmentation, right?
Yeah,
segmentation.
we used some other model. I don't remember the name. Masker CNN.
Хорошо.
And
So did you guys learn these models very well? Did you learn their hyperparameters, the training, the configs, all of these things?
There were configs, but we didn't really go in deep.
Nice. So in this course, we will go very, very deep to every single one of those configs. We will go not through just one version of YOLO. We will see all the versions of YOLO, and we will speak about, of course, faster RCNN and mask RCNN and how can we use them, and most importantly, how can we change them if we need to. Right, so you will have access to not just the configs, but to the model itself. It's written in PyTorch. So how can you access the layers and how can you change the layers? How can you change the training process and all of that? Then the next one will be transformers. So first, before going to transformers and attention, we will speak, or in transformers and attention in visual setting, we will speak about transformers in natural language processing. So I still didn't prepare this lecture, but probably we're going to start speaking quickly about RNNs and then LSTMs, and then we will go through attention. The lecture should be quite easy. I'm not going to make it very mathematically heavy, but we will. Okay, somebody raised their hand, please go ahead. Yeah.
Yes, what is the word in advanced in CV?
Yeah. For some reason, when I'm doing the presentation on this iPad, the words are mashed together, but the first word is liquid neural networks.
Thanks.
You're welcome. So let's just come back to transformers. So as we said, we will have one lecture about transformers in natural language processing, and then we will have a lab on how can we use BERT to do basic natural language processing tasks, such as, well, we will see. Probably not going to do anything from sequence to sequence. We're going to stick to things such as sentence classification or something like that, or emotion classification. Like, yeah, you just take a tweet and you tell it if it's a negative tweet or if it's a positive tweet. So it's going to be something pretty easy because that's not the point of the course. Mainly the point of it is to give you the theoretical knowledge about attention, such that when we go to visual attention, you will understand it much simpler. And then, of course, we will study the visual attention by using, of course, visual attention, DEIT, and SWINTY. So SWINTY is the current best model for object detection and image classification. And it's a very interesting model since that I find very useful for you guys, because any contribution in this model in these days can be easily published in any research conference out there, right? So it's a very new model. The hype is really in there, and any contribution of just basic baselining it against different other models and showing if it's actually better on specific tasks, that would be a very good contribution already, right? So if somebody just comes up and say, I'm going to baseline AlexNet, that's not going to be a good contribution, because we already know AlexNet was good at its time, and now we have something better. But benchmarking and SWINTY can be a very interesting thing to see, just seeing it on different tasks, for example, object detection and image classification. That's a good research paper for those who are trying to find ideas. And then we will speak about advances in computer vision in general. I took an example of liquid neural networks, which is an idea that was presented by some MIT students, or MIT's lab. And it's a new way of building neural networks, and I think it's very important. So usually we have so far CNNs, which have dominated the field of computer vision. And now we're trying to, or the trend is to get new ideas into the field to replace CNNs by things such as attention and transformers and liquid neural networks. So the goal of this course, we will have, during this course, we will have different presentations, quizzes. We will have, of course, homeworks. The homeworks are going to be very easy if you just pay attention to the lab. And of course, we're going to have the final presentation, which is a paper. Or in the case of some other students, it's going to be a project presentation. And of course, there will be a midterm and a final exam. I'm thinking maybe we should combine both oral and quiz format. So something like you have done in the final exam of Introduction to Computer Vision. So something like that, but not for 1 hour, but just for 30 minutes. And then each student would just hop on to a Zoom call with me, and we will have a small conversation about computer vision and stuff like that. The questions are going to be very easy, just to make sure that you guys know the basics of the course. And that will be your grade for the midterm and final exam. There will not be a practical midterm or a practical final exam. The practical part will be evaluated basically by the homeworks and by your work on the project. I see that Maxime has raised his hand. Please go ahead. Yeah.
Will we have breaks?
Certainly, yes. We will have lots of breaks, especially since it's like 4 hours and a half consecutive. That's a lot. I understand that it's too much. So yeah, we will have lots of breaks. Please, whenever you get tired, tell me. We can take like a 5 minutes break. And of course, between every one lecture and the other, usually there is a 10 minutes break. Within the same lecture, we can have some several 5-minute breaks.
Thanks.
Thank you. So now that this is done, I was prepared to like spend some time to getting to know every single one of you. But since we already know each other, let's try to make this a bit quick, right? So please go ahead. If you have not taken the Introduction to Computer Vision course, please go ahead and just give us a small presentation of yourself. Let me see who did not. I think it was Mauricio. Yep. Mauricio, if you are here, can you please like tell us who you are, what you have done, what is your background, and things like that?
Me, right?
Yes.
Okay, my name is Mauricio. I am from Colombia. I am doing the master in data science, and my background is physics.
Cool. You are a first-year student or second-year student?
First year.
So this is the first-year student. You took the course with Professor Khan?
No.
How? I think the first-year student of Masters in Innopolis should take a course with Professor Khan on machine learning.
Okay, I'm taking it right now.
Yeah, you're taking the course right now. Just to make sure, what did you guys cover?
Right now, the last lecture was about CNN.
Okay, so you know CNNs, you know neural networks. That's nice. Okay, that's good. I see Maxime is raising his hand. Please go ahead. Yep.
Sorry, it was from the previous question.
Okay, nice. So for the other guys, can you just one person or a couple of other people just present yourselves? Tell me what is your background. Tell me what are your expectations. For example, one person could represent data scientists. Another person could represent, I don't know, robotics or something like that. And one person would be for research and one person would be for industrial applications. Just you, who you are, your background, and what are your expectations from this course?
Okay, so my name is Lev. I'm from software engineering track, and I don't have much of a background in machine learning except for this course that we took with Professor Khan. I believe it was in 3rd year.
Nice.
And mostly like not really interested to go deep into machine learning and object detection, computer vision, and all that stuff. But I am interested in having this kind of like toolkit that I can use in every day. So just something that maybe is already done, like using already existing classifiers, but
Yeah.
actually putting them to use to solve my problems. So yeah,
Certainly.
that's what I'm looking for from Scrum.
One small question. You must, as a software engineer, you must be familiar with either mobile programming or web development. So which one are you? Which area are you working on?
I'm a web developer.
You're a web developer. That's awesome. So for web development, which web developer? Like front end, back end, React? What is there?
Front end mostly, and
So
the
you're
framework is
front.
Svelte.
Okay, so you're front end developer. Okay, so we could have a very good application for that, right? So are you good with anything like backend, right? Just basics of backend.
Yeah.
Good. So we might have like a project for you to deploy an object detector for front end, right? So for object detection, there are so many libraries that can be, or for machine learning in general, right? There are so many libraries that you could use in front end, and there are endless libraries that you would use in the back end. But for the back end, we're gonna try to make it very simple. We will go to the front end and do the majority of the work there, okay?
Sounds cool.
Nice. You will see what are the different models that we will work with. Preferably use something either for object detection or for image classification, and just try to use it in different ways. So the easiest thing I can think of right now, let's say, is like yoga poses matching, right? So for example, you take an image of a yoga pose, and you just ask the user to perform that yoga pose using the camera, and you will just judge how close are they to the correct yoga pose, right? So you just tell them, adjust your leg, adjust your hands, or like do something like that, right? So this is like the basic I can think of.
All right.
Sounds interesting for you? Of course, not just the yoga, but you could do it whatever you want, right? So instead, if you're not interested in yoga, maybe you could do something like what's it called? Basketball. So for example, somebody would just shoot something at the basketball, and you would just tell them your stance is not correct, you're not looking directly at the ball, or something like that. I don't know. Whatever your main hobby is, you could try to combine machine learning with it. Хорошо?
Yep.
Отлично. So anyone else, just especially for those who did not take Introduction to Computer Vision. So please go ahead. All of you guys must present yourselves. Those who have taken the course of Introduction to Computer Vision, so I at least know some of you, we will have a very short introduction in the end. Anyone else who did not take Introduction to Computer Vision? So for example, Ozzy, I don't remember you took the course.
Yeah, I did not take the course. I'm also in the software engineering track.
Nice.
I think same as Lev, the only background I have was with Professor Khan, like Introduction to Machine Learning. And
cool.
I mean, not that I remember it in detail, to be honest, but yeah, that's about it.
And are you like web development, mobile development, something like that?
I'd say I'm a junior in both. I didn't choose which I want to pursue fully, so.
Okay, which one do you prefer the most? Which one are you most comfortable with?
For now, web.
Yeah, web is easier because you don't have like Android Studio and all the other problems that you would get. Yeah, I remember mobile development was a big problem, especially you had to keep like an Android and an iPhone next to you to test them, and compilations was always a problem. But web development is much easier, right? So you can choose either one of them, and yeah, do something, same thing as Lev, right? Just try to come up with an idea to combine machine learning into a product that users can use. Yeah, I'm gonna try to judge you guys on whether the product is beautiful or not. So try to give it a very beautiful front end, and make it pretty like UI and UX orientedly beautiful, right? So something that is easy, something that is intuitive, and not super ugly on the eyes. Хорошо?
Yeah.
Anyone else? I think I remember the major. Artyom. Artyom, you were in introduction or no to computer vision?
Yeah, I was, if you hear me.
Okay,
you
so
hear me?
everybody, can you, yes, I can hear you. Nice. So everybody else has taken the introduction to computer vision course. Can you guys tell me what are your expectations from this course? So are you someone who is going to stop at bachelor's and go directly to work? Or you are somebody who wants to continue towards their master's and want to, you know, broaden up your field or your options for doing a PhD in some cool university?
Start
Or
with
master's,
bachelor.
I mean. Mm-hmm. You're just doing a bachelor's. Anybody else who wants to go for master's here?
I think we can make a poll for that.
Yeah, we could definitely make a poll for it, but I just wanted to get like one profile that kind of represents the rest of the guys who want to do their masters either here or somewhere else, and just see their understanding, right?
Okay, I want to do my master's.
So
Then.
Good. You want to do masters in, and you are in, nice. So you want to do your masters in machine learning or data science, or you
Yeah,
want to do something else?
Data science, yes.
Okay, got you. Anybody else who wants to stop?
Same for
I
me
wanted-
as first one.
okay.
I want to continue and do my master's.
In data science, okay?
Yeah.
Good. Yusuf, I think?
Yeah, I wanted like to say my expectation of the course. So we had the introduction to computer vision, which we had
Yes.
like the basic computer vision techniques and some basic models.
Yes.
My expectation for the advanced one is like the more advanced models, of course, and how to train like new models or like basically, for example, in a competition or in a job or something like that, they develop new new models.
Yeah.
Although it's not like, even if it's not like completely new, sometimes they combine a couple of models or like use a backbone and the head and like combine different models and do some weird stuff. So I was expecting to see what is done in the industry level of computer vision.
Oh, you would be very disappointed in what's being done in industry, right? Because the industry is requires something very stable. Even though you might have an idea that gives good results or works very well theoretically, experimenting with it and trying it is not something that is going to be done like in the industry very fast, right? So industry is usually very slow in adopting newer and newer models. So for example, just at Google, right? So they invented BERT, and just at Google, they did not accept to start using BERT until like a couple of years after BERT has gotten its like complete reputation and was trained millions of times and have been used very, very much in a majority of cases. So this is like the problem that you would see in the industry. Usually they're very slow at the adoption of new models. So if you want to do industry stuff, you're going to want something that is very reproducible, something that is very stable, that's always, you can trust it, even if it's not very good or very performant, it is reliable. So this is the most important part. But certainly we will cover the majority of what you guys, what you had just said. So just the combination of different models, take this from that, take this from that, and then just build a new model that works for you, right? Хорошо?
Good.
Anybody else has a different maybe expectations that they would like to share?
Yeah, maybe I can speak up. I'm one of the students who's going to finish his bachelor and do not work in the field of machine learning and deep learning and stuff.
Yeah.
I visited the course of Introduction to Computer Vision. We learned some basic stuff there and had the practical exercises. Here I expected like to get more of the theory, like in the similar way that we did, and get like similar practice tasks as we did in labs, because they were kind of useful without like without going too deep into the industry or research areas, because I don't really need them. It's just like, I mean, I tried to study computer vision on my own, but it turned out to be like really hard, and introduction was really great. So like, just to get some experience without reading 50 articles in the morning and 50 at night. Just something
Yeah,
like
I
that.
got you. I certainly get you. Yeah, I understand you. So this is again, this is like an elective course. So usually elective courses are pretty chill, right? You don't have to do a lot of work. I remember most of my elective courses in Innopolis, I just attend and do something else and not listen to the lectures at all, and or just attend and not put any pressure or work on it, right? So usually elective courses are very chill. We're gonna try to make this one as chill as possible, right? So please feel free to share memes. So this is something that you will be graded on, or you get bonus points. If you share some meme that gets lots of attention and that is pretty funny, you would get bonus points. So this is something that's funny. But will I require lots of work? That depends on the student, right? So I will ask students who are interested to put lots of work because they want to. But the students who just want to learn basically just the basics and would like to get some theory and take it as chill as possible, I would not have too much of expectations on them to weigh them down, especially for those who just do not want to continue a career in computer vision, but they're just mainly interested in understanding what it is and just being able to communicate with other people who work in computer vision, right? So if you are going to work in the industry or any company, usually you're going to have some colleagues who work in computer vision, and you're going to have to communicate with these people. For example, understand what is the input to their models, what input they require, what output will they give you, and how can you treat that output. So yeah, just as long as you can understand their language, it's pretty useful. Anybody else who has a different maybe expectation or who have a different way of seeing this course? I see. Sun, one day you'll go up. That's pretty interesting. That's pretty funny. Let me see. Where did you get this one? If there's like some channel or something like that, that's pretty funny. I like that. But you
From
sadly
the depth
cannot.
of the internet.
From the depth, you would not get a bonus point for this one. You need to like.
Oh shit.
Up. Your
I'll
game
take
a
it
little
back
bit.
then.
No, save it, keep it. But you need to like put some effort in it. It needs to be very, very funny. But this one's pretty nice too. So yeah, for those who are like afraid of like, mathematics or maybe think that the field is pretty difficult, it's not. It's actually very simple. And we will see all of these ideas. They're very logical and very intuitive. And we will try to do lots of revisions as we have done in the introduction course, just to make sure that the student is remembering as much of the information as possible, right? So the goal of this course is not to just give you something that you will forget about in the next 2 years or next half a year, but to just give you intuitions or change the way of your work. I would really be very happy or very glad to see you guys changing some things in your everyday work style. For example, using things such as Trello, using things to organize yourselves, using mind maps, changing the way you take notes. So all of these things are very important for the rest of your life. And honestly, this is the main goal of this one. So just to make sure that you guys are equipped with enough tools and enough experience to either do research on your own or continue in the industry without facing too much of a change in the rhythm from what you are seeing in the university and what you will experience in industrial work. So I think we have seen the majority of the students. We got to know each other. So we can just go ahead and start the first lecture. Before I go in, I would just want to confirm that how is the comfortability of how comfortable are the students with things such as CNNs, right? For example, for Ozzy and Lev, are you guys very comfortable with CNNs and stuff?
I know what it stands for, but that's about it.
Хорошо. So, sorry, we're gonna try to go through this lecture pretty quickly. So it's going to be a simple lecture on image classification. If we advance fast enough, we will go to the, what is it called? Just a quick overview of 7 of the most popular image classification models, which are AlexNet, ZFNet, Inception or GoogleNet, VGG, ResNet, ResNext, and PNS18SNet. It's a very, I hate that the name. So we're going to just go through all of these architectures, describe what was new in each one of these architectures, and just see their performance. After we finish this lecture, we will go to the lab, and hopefully the lab will be pretty simple. I will just show you guys how to do basic image classification, transfer learning, and just give you some tips, right? Anything you guys want to ask, you can just go, feel free and ask it, right? So let's start. I hope that on the iPad, the presentation does not change that much. Screen share, start broadcasting. Can you guys see my screen? Everything is shared, right? Oh, okay, nice. So now I actually can't see what you guys see. That's good.
We can see the screen, but not you.
Yeah, for some reason, every time I share the screen, my picture just disappears, right? Okay, let me just go back to Zoom. My picture comes.
Yeah.
I leave Zoom, my picture disappears. Genius. Like, you know, technology is pretty surprising sometimes. So anyway, I will try to solve this problem as fast as possible and just make sure that my video is visible while I'm doing the presentations.
It will not work well you using iPad.
Really? So there's no way I can solve this problem, huh?
It's even in FaceTime, it's working like that.
Okay, got you. Yeah, sucks, but that's okay. I think we can quickly just, or maybe next week's, we will just go back to using laptop. I'm gonna give up, or maybe use the iPad for annotations and use laptop for video. We will see. So the content of this lecture is gonna be pretty simple. I'm sure the majority of you guys have already seen this lecture, or did we do this lecture before an introduction to computer vision? These slides, right? I'm sure I've done something like this, at least. No?
Well, it will not hurt if we recap these things anyway.
Хорошо. So in this lecture, we will speak about neural networks in general. Before we go to neural networks, we will just describe some of the most basic terms that you would see in machine learning. And then we will just advance a little bit to convolutional neural networks, what they are, what they do, the logic behind, but not the mathematic, right? So just the basics, just the intuitions. And then we will speak about some tips for training CNNs. First part is going to be about neural networks, or most importantly, multi-layer perceptrons, which are fully connected neural networks, and they are the first architectures that were used in the field, and they provided a great increase of performance over traditional machine learning, especially support vector machines, which at the time were the best thing that they had. So neural networks kind of took over the field of machine learning, and CNNs have taken over the field of image classification for the last, I think, 10 years, like 9 years and so. Only CNNs are what's being used for any object detection or any image classification task in the industry and in research. But now we are slowly recognizing that we have reached the limits of CNNs, and people are trying to come up with new ideas to solve this problem. Let me just close this like that. Nice. So in this first part, we will speak about what is classification, what is regression, what is supervised, what is unsupervised learning. We will try to give a small introduction to what is semi-supervised learning, or what is self-supervised learning and active learning. But these are concepts that we will see, I think, I think in like the 5th week of this course. We will definitely start to speak a lot about self-supervised learning. It's a very interesting concept that is coming ahead in computer vision and natural language processing also. So definitely worth looking at. Second thing, we'll speak about logistic regression. I'm sure all of you guys remember logistic regression, but we will kind of look at it from a different point of view. So there are many, many ways of logistic regression. I remember when we were doing our masters, we studied logistic regression in 4 different courses, and each one of these courses gave a completely different presentation to logistic regression, or a completely different point of view about logistic regression. So it's a very powerful model, and in this case, we'll see how does it relate to neural networks, right? And basically, throughout the rest of the course, I'm going to be using the term just a simple logistic regression in every single step of all of these different models. And the final part, of course, is to speak about different loss functions such as mean squared error and cross entropy. Yeah, so before we go ahead, I would just like to ask the students who did not take the introduction to computer vision, so the non-data science students, what do you guys know, or what do you guys think of when we say the terms regression and classification?
Classification is assigning labels to objects.
Nice. And regression?
I don't know, some sort of descent.
Regression is just assigning a number to an object, right? So classification is assigning a label to a concept, whereas regression is assigning a number, a continuous number to an object, right? So for example, different examples of regression would be price detection or price classification, price recognition, price, how do you say, price detection? Prediction, yeah, price prediction, sorry. So we just predict the price. You just give it a picture of a house, or you just give it the information about certain house, and it will tell you what should be the average price of a house like that. Some things like detecting or predicting the temperature, predicting the age as a continuous value, and of course, for classification, we could predict what is the class of a certain image. So for example, if it's a car, is it a vehicle, is it a motorcycle, so on and so forth. We could detect the type of the animal, the type of a plant, for example. And of course, the most famous example is digit recognition, which is like taking a handwritten image of a number, and we try to say if it's 1 or 2 or 3 or 4 or 5 or 6 or 7. So on and so forth. Now I'm going to open a new bracket and ask you guys, what do you understand when I say supervised learning? And what do you understand when I say unsupervised learning?
Which bracket?
Go ahead, just anybody try to, especially for those who do not really know or who are not from a data science background. I'm sure data scientists, like you guys already know all of this, but for non-data scientists, this is pretty important to just get your brains bit working with us, like to make sure that you guys are focusing throughout the lecture, right?
So should data science people just keep quiet during the lecture?
No, of course not. I'm going to ask lots of questions which are a bit more difficult than these. So these are definitely for the data science guys.
Okay, so supervised learning is when we provide labeling to the model. And unsupervised is when we want the model to figure it out by itself.
Got you. So let me give you some examples. So classification and regression, is it a typical thing for supervised learning or a typical thing for unsupervised learning? When I say typical, it's the majority of the cases, because now with all the different advances of research, you will find both of these concepts in supervised and in unsupervised. But typically speaking, where do you find them the most?
Supervised?
Yeah, in supervised learning. That's good. So another very simple question would be, what loss functions do you use for regression, and what loss functions do you use for classifications? So just to maybe give you a simple, just so you guys know where we are working. So here we see things such as mean squared error and cross entropy. So can somebody tell me, where do we use mean squared error and where do we use cross entropy?
Cross entropy when you need to distinguish between two. Is it binary? Not binary cross entropy. Then you need to distinct classes between each other. In MSE, when you need to calculate the error between the target and the between the output and the target.
Got you. So you're saying
not between
MSE, yeah.
Not between the classes, but between the target and I mean, in MSE there is no relation between the classes, and in cross entropy you calculate the relation between the classes.
I like this way of thinking. You really like this one. Yeah, I really like it. So you're saying MSE, you don't care about the relationships between, for example, the predicted pixels or the predicted values, if it's not just one value, right? Whereas in cross entropy, you do care about this relationship. You do model this relationship in one way or another. That's an interesting way. Typically, where do you see mean squared error? Do you see it in classification or in regression? Typically.
Typically, MSE is regression and cross entropy.
Very well. For classification, nice. So you said that there is binary cross entropy and cross entropy in general, right? So yeah, cross entropy in general works with lots of classes, and binary cross entropy works with 2 classes only. And of course, cross entropy. Can you guys tell me, what is it calculating? What is it doing, right? So what is cross entropy, and why is it related to entropy in general, right?
Cross entropy calculate entropy between each pair of classes.
Okay.
So we can say that cross entropy contains binary cross entropy inside it, but for,
yeah, of course.
But for each pair of classes.
Can you tell me what is entropy? So you did describe entropy. So what is it?
How in simple words, it's how distinct our classes are.
Good. Very good. Right. So for example, I think this example all of you guys have taken. So you take a decision tree, right? And you just keep on splitting. Every time you split, you get the new data, right? So here you have the samples that satisfy this, what is it called? This condition. So here, for example, we have 3 class 1 and 5 of class 2. This is not a very clean cloud or clean data. Whereas here we have a much cleaner data with 5 of class 1 and 0 of class 2, right? So this is much cleaner. You can take this concept a bit further by thinking about these as just probabilities, right? So if you belong here, you should be, yeah, this is a bit difficult. I chose a difficult one. So 5/8, how much is 5/8? 4 divided by 8, 0.5. Let's say it's 0.6, right? So you can think about this as 0.6 belonging to class red, 0.4 belonging to class green. So this now are the probabilities that are given by your, what is it called, by the model. And you calculate cross entropy on these values is the same thing as calculating the entropy of this beautiful node in your decision trees. So I'm sure Professor Khan has taken you through calculating entropy as a way of finding or evaluating the different, what are they called? The different conditions, which ones are the best in terms of information gain. So if you guys would like to have a small revision about these concepts, we could do it together, I don't know, like on an extra lecture. But for today's lecture, we will just assume that the majority of you have taken the course with Professor Khan and remember at least some basics about what is cross entropy, what is decision trees, and information gain, and so on and so forth. Is my assumption correct? Do you guys remember all of these concepts? The silence is saying a lot. Yeah. I would assume that nobody remembers all of these concepts. So maybe we would have like just a quick recap about all of these different loss functions during this lecture at the final, right? So the first model that everyone has studied in machine learning, which is linear regression. So linear regression, instead of just thinking about it as just a linear mapping from a value to another, let's start to think about it as the following, right? So linear regression, the formula is the following. So this is height. This is height. And we have built a way of converting the width or the weight, yeah, the weight of a person into his height or his height just by performing a simple multiplication, right? So just by performing a simple multiplication and summation, we managed to convert a concept of weight into another concept of height, right? So this is what linear regression is actually doing. So linear regression is learning different concepts or mapping different concepts from their input into the output. In this case, we are learning a mapping from weight of a person to the height of that person. Now, this example is pretty simple, and it is only used in regression. Can somebody tell me if we want to do linear regression for classification, is it possible to use it? And what are the constraints or what are the problems that would appear if you use linear regression for classification?
We can, but we need to find thresholds for the final concept, as you say.
Got you. So for example, we take this data set of blue points. You see the blue points? So this is the data set, and we just build our beautiful regression line. So this is the beautiful regression line. This is what we get with linear regression. Okay, let's just put it here. Useless. Let's just imagine that this is the line that we got, and this is the data, right? And your friend has proposed that we put an if statement over this beautiful one. So basically it becomes like this: if y, or the predicted y, is bigger or equal than 0.5, then we return class 1, else class 0, right? So this is what your friend has proposed. Now, can somebody tell me, so it's a linear classifier, right? So this decision boundary in here, the decision boundary that separates 1 and 0, it's a linear decision boundary. Can somebody tell me how does it look like, or where is it put? Okay, just try. Is it this line? This is the linear decision boundary between 0 and 1?
It should be vertical.
It should be vertical. I like this already. So this is not it, right? This is what you're saying. Is it this one? Sorry. Is this the line that separates the positive class from the negative class?
It can if we take, yeah, we can take this.
We can take this one, right? Can you guys vote on it, right? So positive vote would be this one, raise your hand, not raise hand, like this. A negative vote would be just shocked, right? Anybody else shocked maybe, or?
I don't understand why are we talking about lines when the data is one-dimensional?
Oh, I like that. I really like this answer. I really like this question. And this is the trick about the question, right? So keep in mind that the data is unidimensional or one-dimensional. And tell me, where does this linear decision boundary, or what does this linear decision boundary look like? I like what you're saying. So
it should be, shouldn't it be vertical, like perpendicular to the horizontal line?
Okay, so you're saying this is not it, right?
No.
Okay, let's delete this one. Does it look like this? I don't know.
It depends on the idea how we distinct classes from the linear regression.
Yes.
Exactly.
Okay, so I said we are using this kind of model. If, sorry, let's use a different color. If y, or predicted y, is bigger or equal than 0.5, then it is 1, else then it is 0. So this is the decision boundary that we are creating. Can you tell me, how does it look like?
So anything to the right of y, since it's a line, it's a straight line. So the point where the line crosses 0.5, anything to the right would be classified as one class. Anything to the left, it would be classified to the other class.
So you're saying this is the decision boundary?
Yes.
Very nice. This is a very good question, and you have provided the correct answer. So as your friend has said, the data is unidimensional. So any decision boundary that should act on it should be only on the x-axis, right? So the decision boundary is just this point. And since all of these points are actually just, in fact, just laid around here, this second dimension does not exist. So this is the decision boundary. This is the point of the decision boundary. All of this is class 0. All of this is class 1. This is pretty important because the majority of the students that I taught usually confused this concept a lot and didn't understand what is a decision boundary. But thankfully, you guys are pretty good at that. Nice. Yeah. So what is the problem about using this model, linear regression, for classification? So just throw around all the problems that you guys know. I'm sure you're already familiar with all of these problems. So just throw them directly. I'll just give you some hints.
Sorry, can you repeat the initial question?
What are the problems in using linear regression for classification?
More than 2 classes.
Can you repeat, please?
The output of linear regression is unbounded.
Yes, the output is not bounded. So you would have values such as minus 550 and plus 20,000, right? What does it mean, plus 20,000? So this is the first problem, which is being unbounded. Why do we need something that is bounded?
What's the problem in that?
Exactly. This is the next question. Why is this a problem? if it's unbounded, why is it a problem for classification?
I think it affects the loss because when it says like 1 million and the class is 1, and on the same point, on another point that has the same class, which is 1, and it says 10. So if we use MSE with regression, so here the difference is 9, and here the difference is 1,900.
Got you. Very good observation. Using MSE with this setting would just give very huge problems, and you might not be able to train it at all, right? Another setting or another answer would be?
It's about the concept of probability.
I really like this answer. The concept of probability, right? Why the concept of probability is very important? Because for us in classification, what we are trying to do is we're trying to predict what is the probability of this object belonging to this class. This is a very important concept that will help us to understand the output of the neural network. So the neural network will give us some answers or give us some predictions. We would like a human being to interact with it, right? So the human being will look at these answers and then make some decisions based on those answers, right? So the goal here is to have this concept of probabilities to make it easier for a human being to interact with our model. So unbounded makes the probabilities useless. So if I tell him a probability of 1 billion or minus 25, makes no sense for him. But if I tell him the probability is 0.6, he understands 0.5 is very small compared to 1. But if I say the probability is 1 billion, is it big or not? This is something that he would not be able to tell because the values are quite unbounded. There's no way of saying if 1 billion is big enough or it's not, right? Or if it's too small and we should just discard it. So this concept of probability gives us more insurance about the results of the model and more interpretability in the results of the model.
But actually, couldn't we regress the probability? I actually read one paper about that. At the end, you don't get always a probability between 0 and 1. You could get a little bit of negative or a little bit of above 1, but it's not that much. I don't remember the problem that you were trying to solve, but I think it's also doable.
So you're trying to say we use MSE on probabilities?
I don't remember which laws did you use, but we can use that. Yeah, like so MSE. So the line, it doesn't have to be a line. It could be like a polynomial regression. It doesn't have to be a linear regression.
Gotcha.
And it can regress the probability of the classes.
Yeah,
so we have a hyperplane
doable.
that is wiggly, basically.
Gotcha. So can you tell me what did they do, right? So they took this y equals ax plus b, and they converted it into something else. So you said that
Again,
they
I
kind of
couldn't hear you.
You cannot hear me? Can you guys hear me?
I think my internet is bad.
Can you hear me?
We can hear you, yes.
Now I can.
Okay, хорошо. Yeah, so we took this ax plus b. How did we convert it, or how did you convert it in your example? You said we, instead of using this simple function, we used something that is a bit more non-linear, right?
Yes,
can you
for
tell
example,
us?
we can use a sine function plus something like resize it. It can be something like that. So we can punish the model more on when it gets something outside of between 0 and 1.
Yeah,
stuff like that.
that's definitely doable, right? So this is one way of doing things. But for the sake of this beautiful lecture, we will go with the simplest of activation functions, which is
Sigmoid.
Sigmoid, right? So the beautiful sigmoid function will take any value between minus infinity to plus infinity and map it into a value between 0 and 1. So this is why our beautiful sigmoid function is pretty useful. it can convert linear regression from a simple term like this one into something that uses probabilities. So now that we have seen all of that, we can summarize the logistic regression algorithm as the following. As the following: if f of y, which is f of ax plus b, bigger or equal than 0.5, return 1, else return 0, right? So this is our beautiful logistic regression, and this one is a simple sigmoid function. Just a final question: is this trained with traditionally? Is this trained with what is it called? What is that one called? Binary cross? Yeah, cross entropy, or is it trained with something something such as what is it called? MSE. Yeah, very good question. How is logistic regression trained? If you guys don't know the answer, then we will just skip through it directly.
I don't.
You do not.
It depends on the implementation.
Right. In sklearn?
Doesn't it use like SGD or something like that?
Yeah, it uses some of these weird solvers. Yeah,
like gradient descent, or
they're quite similar to what you would expect of gradient descent, but they're more of Newton optimization techniques. You might take an elective course on optimization and you will study that in that course, but if not, then just completely ignore that it exists, right? Now we will speak about the first step towards building our neural network, which is perceptrons. So perceptrons, this is what I will be calling from now on logistic regression. Perceptrons are just like a fancy way of saying logistic regression. What they do is they take their inputs, multiply it by some numbers, so y equals ax plus b, add some bias, of course, you're already familiar with that. They do the summation between all of these different values, and then what they do, they apply some activation function, as we have seen before, which is just a function over this value. Very simple technique, and it just ends up being our beautiful logistic regression, right? So what you see in here is just another way of saying logistic regression. This is what perceptrons are. They do not provide any more computational techniques over logistic regression. So it's a very simple concept. They work because they are working as logistic regression. And as we said, logistic regression, its strength is that it can map a concept from one area, from one, let's say, weight, into a different concept, which is, let's say, height, right? So this mapping is very useful. We're trying to map or create different concepts that would help us understand the data better, that would help the network or the model understand the data better. This is why perceptrons and logistic regression are very useful. Just this simple technique, behind it is happening a lot of, let's say, understanding of the concepts and understanding of the data. So where does this understanding come from? It comes exactly from our previous example of mapping the height to the width or to the weight of a person. Now, a very simple or a very logical expansion of logistic regressions is the multi-layer perceptron, right? So we saw that mapping once, so mapping from height to weight was very useful. So the next idea would be, how can we repeat this mapping multiple times in order to learn more complicated concepts and perform deeper understanding of the object, right? And this is what multi-layer perceptrons is doing. So the first way of building this, let's ignore this beautiful neural network. But the first way to do it would be to have one logistic regression in here. So you have this first concept, and then you just continue mapping it into a second concept, something that is a bit deeper, right? Then you continue mapping it into a third concept. Then you continue mapping it into a fourth concept. And hopefully this fourth concept is so complicated and so rich in information that you would be able to perform your classification much easier than you would on the first concept. So this is what neural networks have done.
I'm sorry,
And
can I
then-
ask a question?
Yeah, of course, go ahead.
Why are we talking about logistic regression as a regression technique? I thought it's more of a classification technique.
It is a
So-
classification technique.
So in classification, we don't map a concept to a concept. We map a concept to a label.
Yeah, what is a label? Let's come back just a little bit, just once in here. What is a label? So let's take, for example, this is the weight. This is the weight, and we map it into income. Let's say rich or poor. So based
No,
on the weight,
I get how these values are then converted into labels. It's just
Yeah.
that it feels like you were talking about logistic regression and perceptron as a way of mapping one concept into another. And I
Yes.
thought by concepts you mean like actually I don't know, like continuous ranges of values, not just discrete labels.
yes,
Is that not what
and
you
no.
meant?
Yes, exactly. This is exactly what I meant. Remember what logistic regression is? It's just a fancy linear regression, right?
But
So if you
not
understand,
exactly, like
well, it's
they
just
are used for
linear
different
regression. Yeah, it's just linear regression, but bounded, right? This thing is just the same as this line, but instead of allowing it to just have different values, we are forcing it to be in this range. So this is what logistic regression is. It's doing theoretically, or for our purposes, for the purposes of this understanding, linear regression and logistic regression are doing something very similar to each other. The way we are using it is we are using it to map from one concept, initial concept of input, weight, into some different concepts. Now, the neural network does not have concepts that we understand, like, for example, rich or poor, or like the richness of the person, but it will develop its own concepts, right? So it will develop concept 1 or concept X. This is not a humanly understandable concept, but this is a concept that will help the neural network make its classifications. Did you get this?
Oh no.
Not really. Nice.
Yo,
No, that's okay.
wait, do you hear me?
Yes, I can hear you.
Oh crap. I just
No,
like
no worries.
no, I cannot seem to get back into the Zoom call. Oh yeah, never mind. I'm here. I am. Yeah, I understood. Sorry
Gotcha.
for that.
Nice. That's okay. So try to think of this perceptron, of this logistic regression, as just a way of mapping from one concept to another. This is like how we are going to see it. So remember what we just said. We did a very simple trick. The neural network will build concept number 1, map it to a more complicated concept number 2, map it to a more complicated concept number 3, and so on and so forth, right? So this is like the logical explanation or logical step forward over logistic regression. Instead of mapping to one concept directly, we map to multiple concepts, make them more and more complicated, make them more and more interesting and more useful. Now, how do we build this multi-layer perceptron is by extending this idea even further, right? So remember when we took the weight concept, weight as it is can be mapped into a very large variety of other concepts, right? So we mapped it into how rich the person is. We mapped it into the height. Some person would be able to map this into the gender. Another person would map this into like the country where you are from. You can extract a lot of information from the same value, right? So this is why instead of just having one logistic regression at each step, now this step number one would be calculating lots and lots of different concepts. Each one of these points is a different concept. Now, each one of these concepts will be mapped to even deeper concepts, right? So on and so forth, so on and so forth, so on and so forth, until we reach a list of concepts that are so abstract, that are so rich in information and very useful for classification that neural networks can use for classification or regression and perform very, very good or deep analysis of the object. So this is what you get here from this deep learning or deep understanding using neural networks. So I hope this way of seeing neural networks kind of takes away some of the mystery behind and just make it seem like a way of mapping our input concepts into more complicated. So this is the initial complex concepts, number one. And then we map these complex concepts into something that is even more complex. So this is complex concepts number two. And complex concepts number two are a lot more rich in information, a lot more rich in abstractness over these first set of concepts. And we repeat this so on and so forth until we reach a very, very deep understanding of that object. Do you see neural networks in a different point of view now? Or at least understand them in the first point of view?
Yeah.
Nice. Now I want to ask a simple question. If each one of these different points or each one of these values was just a linear regression, sorry, all of these were just linear regression and not logistic regression, right? So meaning there is no non-linearity, there is no activation function applied after each one of these concepts. Does that increase the complexity of the values we are calculating, or the complexity would always stay the same?
No, it doesn't, because it stays linear.
Exactly, right? So this concept right here is just a linear combination of these concepts. This concept is as complicated and as useful as each one of these concepts, right? So it's pretty useless for us. There is no point in building a very deep neural network that does not use activation functions. So the ability to build bigger abstractions is very, very dependent on these activation functions. Why? Because they allow you to build a different point of view, right? So when you take the data like this, so this was the data, you apply it to a nonlinear function. Now the data is looking much different, like the order of the instances is much more different. If you apply another nonlinear, what is it called? Another nonlinear function or transformation from the space of these points, which is just these, right? These values, they will transform into something even more complex, right? So here you will find, for example, instance number 2 in here, instance number 3. Here you will find instance number 50, instance number 60, instance number 70. The order of these concepts will change, and you will find that, for example, instances from this side tend to be the same class. Instances from this side will tend to be the same class. So this nonlinear activation functions are helping you clean up this activations or clean up these concepts that you are learning, right? So the more complicated the concepts are, the cleaner they are, right? So usually by the end, you would reach a representation where all the different instances of the same class are clustered together and separated from the other classes. Does that make sense? Why do we use activation functions? Why do we use this nonlinearity to change basically the shape of the data and to learn something even more complicated and something more in-depth understanding of the input.
Yes.
Nice. So I hope in this first half of the lecture, we managed to see neural networks in a different point of view. We managed to see how can we map the data from one concept into another using linear regression. How can we improve over that using logistic regression and take it a step further to classification? How are these perceptrons just another name for logistic regression? And how can we combine these different perceptrons and these different logistic regressions to build our multi-layer perceptrons? So as we said, we build different concepts like this and do the mapping, but instead of having one concept mapping to another, we will have multiple concepts being calculated from the same data and mapping to multiple other concepts. So here we will just have lots and lots in every step, giving you a more in-depth understanding of the data. So I think we have learned, we have taken lots of information so far. Do we have like a break, like mandatory break first? And then we will see if we should take, yeah, we took a lot of time, right? So we definitely took from the time of the break. And I'm not really sure, I'm bad at math.
Let's just take a break and not calculating anything.
Good, I like that. Let's just take a break of 10 minutes and come back. Just eat some sugary stuff. Don't eat a lot of caffeine, just some sugary stuff. Perform some squats or do some push-ups. It will help get the blood back to your brains, and hopefully you would understand a bit better for the rest of this, the rest of this lecture, especially the final part of the lecture where we will speak about the different architectures that won the ImageNet challenge. So see you guys in 10 minutes or more. Just take however you guys want to rest, and rest very well. Let me just close this. Nice. I think now you guys can see the picture, right? Or not yet? Still not yet.
Not yet.
Yeah,
Now,
now.
yes.
Now, yes. Okay, nice. Very nice. So see you guys after you rested.
Oh, we cannot hear you.
Still cannot hear.
No, still cannot hear you.
We still cannot hear, I think.
Now can you guys hear me? Yeah, now I'm sure you guys can hear me, right?
Yeah.
Yep.
Okay, nice. So at least starting again works. So in the next part of the lecture, we will speak about convolutional neural networks, and then we will speak about the most famous architectures in convolutional neural networks. And hopefully we will have our our first lab. I'm not sure if we have enough time to finish the first lab, but we will do our best to cover as much as possible, right? Now let us start with the presentations. And where did this thing go again? No, there it is. Start broadcasting. Okay. Nope. Where is it? There is Canada. Yep. So now we'll speak about convolutional neural networks, which is a very small trick or a simple trick to apply again the same way of mapping these concepts into something else by using these sliding neural networks, right? So convolutional neural networks, what I want you guys to see them as just a simple feed forward neural network that uses this convolution operation. This convolution operation is just sliding through the image, right? So the main difference between them, previously, with fully connected neural networks, you take your input mappings, right? So these are the input concepts, and you map all of them into one concept. And then you take another concept in the same layer here, and you map all of these into the same concept. Now, what they proposed in convolutional neural networks is to do something a bit different, right? Especially for images. So what we have here is an image like this. And what they are saying is this area in here represents one input concept, not just this, this pixel, right? But this group of concepts here is very interesting. This is what we are trying to study. So what they do is they apply logistic regression on this group of pixels, which are close together, this group that represent the same concept, and map it into another concept that is located in the same area in the output, right? So now we don't have just one output concept, but we have an output concept for every single area in the image. Where did this idea come from? It came from the idea that every single small part here, every single region in the input image represents its own concept. So if you combine all of them together, you're not going to have something interesting. But if you combine only the concepts which are, or the pixels which are close together, you might be able to learn more representative concepts about the image. And this is what's happening here. So instead of, as we said, mapping all of these different pixels, all of these input concepts into just one output, we will map every single region into a output concept. So here, for example, if you are looking for faces, we will build, this is what we call as the nose concept finder, right? So this is the nose concept finder. Previously, one neuron gives you one output, right? Or one concept mapping. Now, one neuron gives you what? Gives you an image, gives you a channel. This channel is just a group of concepts that, or just a way of representing the concepts in the image, but it combines only the regional information. So here, for example, at the start, let me just clean this up a little bit more. Clean this up a little bit. Very well. So here, this is the edge concept, and it is represented in the pixels in this area. What we do is we calculate a mapping from this area to a concept in here, and we put the value of the concept in this position. So this is one pixel in here representing the existence of this concept in this point. Now, if we, for example, find a nose, if our model is a nose detector, or our concept mapper is a nose concept finder, so what it will do is, this is where the nose is. All of these areas do not contain a nose, so all of these areas would contain 0, right? Only the location of the nose would contain 1, would contain an activation. So this is what's happening here. Previously, if we were calculating the richness concept, we would calculate only one value for the richness concept. If this person is rich, my AirPods have no battery. That's bad.
We cannot hear you.
I assume now you guys can hear me. Nice. So let's continue the lecture as previously. Let me share the screen, share content. I might get the hang of this teaching online with some time, like with some practice, we will be good at it, right? So yeah, we were saying that convolutional neural networks are very similar to neural networks in general in the fact of in this idea of building concepts hierarchically, like building these concepts on top of each other. But instead of one neuron making one concept, now one neuron will have a map of the concept, right? So this is the input image. One neuron would give you a map of the existence of this concept inside the image, right? So this region in the image, does it contain the concept that this neuron is looking for? If yes, here you will find a high value. If no, you will find a small value. Just as previously mentioned, you take one, so in each layer, you're not gonna have one neuron, you're gonna have multiple neurons. It's very sad that you guys cannot see me because I do teach a lot with my hands and expressions, and they're pretty useful for understanding, but let's imagine you guys are seeing me, right? And I'm not just waving my hands randomly in the air. So yeah, so as we have said in neural networks in general, every layer does not have just one neuron, but every layer contains multiple neurons. So in this case, where we have one neuron, we have just the input as a map of existence of concept. right? We will have multiple maps as we have multiple neurons. Every single neuron would give you a different map of concepts. And here, what you will end up with is a very ugly image if we continue working like this, but you will end up with the following. Let's just clean this up a little bit. Nice. You should end up with the following. You have just one image in the start, and you will end up with lots and lots of concept maps. These concept maps are commonly referred to in computer vision field as feature maps. Or activation maps, right? So these different words or terminology, this is the terminology used to refer to this, or what we between us understand as concept map, right? So this is a way to represent the existence or the location of the existence of different concepts in our, what is it called? In our original image. So this is the only big difference between convolutional neural networks and fully connected neural networks. It's the fact that neurons now do not operate on the whole image, but operate only on specific or consecutive connected regions of the image. So now this region represents an initial concept from the input, goes through the neuron, and the neuron would give us one activation. Take this one, the neuron again gives you another activation, and this will give you the activation map, or this will give you the concept map. So this is the map of that the neuron is learning from the input data. So now you can see that this neuron, its weights, as you remember, so the neuron is just logistic regression. Logistic regression means that it has its weights, which are this AX plus B, so which are the A and B. The A and B of this neuron will be used throughout the whole image. This is very important. Why? Because these values, or the values that are used to extract different concepts, will be used on different locations, meaning if the nose is here or the nose is here, we will be able to detect it in the same manner. And this is a very important thing in neural networks, in convolutional neural networks, something that differs them from, what is it called, from traditional feed-forward neural networks. It's that at every image, all the weights of the neural network would benefit from the classification, would benefit from the backpropagation, although, or unlike for, what is it called? Unlike for a feed-forward neural network or fully connected neural networks, where each one of these pixels is connected with a certain weight, right? Each one of these pixels has its own weights. So if the nose exists at this region, only the weights associated with this region would benefit from the training, right? So if we, for example, use a feed-forward neural network, and the noses are usually in these two regions, if you test it on a place with the nose in this area, it's not gonna work. So this is the problem with it. But with convolutional neural network, it is gonna work because we are sharing the weights of the nose in this area with this area, allowing the detection to happen regardless of the location of the object. So these are just like some how do you call it? Just an overview of what convolutional neural networks are, why are they useful, and how are they being used. In order to understand this better, there's this beautiful video that I found on YouTube. I'm not sure if you guys can see it very well. Let me try to reduce the speed. I do not think I can do that, but let's see. So as you guys can see, what is happening is we are sliding this beautiful, you see this? This is our logistic regression, right? So this matrix or this kernel of matrix contains the weights of our logistic regression. And what it will do, it will combine or do the multiplication between the weights of the logistic regression here, the pixels or pixel values or the concepts in the image in this region, multiply them together, and it will give you one point or one output pixel in the output or in the concept feature map or in the activation map, right? So this is what's happening here. Let's continue the video. Again, we will slide this convolutional neural network. Can you guys see my screen, my hand? Yeah, you can. We will slide this logistic regression throughout the image. And at each location, we will calculate a value in this activation map or in the map that tells us about the location of the concept of interest. So in this case, I don't know what is this concept of interest, but it looks like it is highly correlated with the existence of pixels in this area. So maybe this is a line concept detector, right? So the concept that we are learning is the existence of lines. A line concept detector, probably this is a line concept detector or something else. Those who took the Introduction to Computer Vision lecture, the goal of all of that course was to help you understand how can we build a line concept detector using just multiplication like this one. And those who have done that, they have seen just with simple multiplication of these values, let's say like this, sorry, 1, 1, 0, 0, just something like that would be able to give you a line detector. They have seen how can we build different edge detectors, different, I don't know, face detectors, stuff like that by simple multiplications. And this was the goal of that course, as I said, just to give you an intuition that yes, with just this simple multiplication in here, we can extract thousands of concepts, thousands of very useful concepts, such as edges, horizontal edges, changes in colors, all of that can be extracted using just a simple multiplication and, of course, an activation function. And then once you have detected all of these edges, you send them through the next layer, sorry, like this, send them through the next layer of, so this was the first layer of convolutions, send it to the next layer of convolutions that will combine these initial concepts to something more complicated, right? So the first layer would do something like different edge detection. Second layer would do concept detection, such as nose, eyes, and mouth. The next layer would combine these concepts with more advanced concepts, such as human face, animal, dog face, cat face, and so on and so forth. And then from that, we will extract even more complicated concepts and basically do the classification on those. So here, as you can see, so we just send our beautiful kernel or logistic regressor through the input image. It will give us a beautiful output. This will give us a beautiful concept map or feature map. And as we said, we do not apply just one single neuron on the input, but we apply multiple of those just to allow the neural network to extract a huge variety of different concepts from every single data source. And as you can see, the training will continue, so on and so forth, so on and so forth, so on and so forth, and we will have it. This is a very beautiful video. I highly recommend you checking it out on YouTube just to see how convolutional neural networks are operating. Now that we know these things, the rest of the lecture will go very smoothly. So as we have said, we have our beautiful kernel. So this is the beautiful kernel. This is the weights of logistic regression. This is the weights of logistic regression. This is y equals ax plus b, right? So this is the A matrix. So previously in logistic regression, A was a vector. No, this is an A matrix. Doesn't really make any difference. It's just different values you will multiply and sum with these concepts.
And so from here, we will have the input. This is the input image multiplied with the weights of logistic regression. We do the sum, put it in the activation map. Very simple, very similar to what we have seen previously. Now, two concepts that come up in learning of convolutional neural networks is the concept of padding and the concept of stride. So padding, in our case, represents how many pixels do we add around the image. So initially, if we take this, for example, so it's, yep. So if we take a 5 by 5 image and we apply on it a 3 by 3 kernel. So can you guys help me out and tell me how many applications will we have of this kernel on this image? So the first application is here, right? 3 by 3. And then the second application is here, 3 by 3. And then the final application comes here. So now that we have applied our beautiful kernel, our beautiful logistic regression weights on the input, we notice that the output will only have 3 values. So there's V1, V2, V3. Let's use the same colors. This is V1. This is V2, sorry. V2, and this is V3. So we can see that the shape of the output decreases. If this is something that you do not want, usually what we do is we add padding. What is padding? Padding allows you to add more values to your initial image. So this was a 5 by 5. Instead of keeping it as a 5 by 5, you increase its size. I hope this will work. Yeah, it worked. So what will happen is the following. You have this input image as the start, but instead of using it, you will add more pixels. Please work. It didn't work. Let's try again. Yep, it worked. So we will add more pixels around the image to make it bigger, such that when we apply our 3 by 3 kernel, the output image will have the same size as this one. Yep, it will have the same size as our input. This is something that is very useful if you would like to apply convolutions a lot of times, because the convolution operation reduces the size. If you apply it, let's say 10 times, you will end up with an image that is super small. So if you would like to apply it, let's say hundreds of times, you might think about adding this padding that will allow you to continuously repeat applying convolutions and still maintain some image form and some image height and width in the output. So this is the goal of padding. What padding is, as we said, is just adding more pixels around the image. So it's just augmenting the size of the output or increasing. The goals of this thing is to either augment, either augment the size of the input of the output or to increase the focus on the borders. So for example, if you are working in an area where the border of the image contains a lot of information. So for example, I don't know, doing some cancer detection or some skin cancer detection or something like that. And for some reason, the most important information is usually here in the borders, let's say. So you would like to increase the focus on the borders by adding this padding, and usually this padding will allow you to include the borders in much more concept calculations. The second concept that appears is the stride. So let's go back to our previous example. This is the input image, and this is our beautiful kernel. It's 3 by 3. We take it and we apply it here, for example, right? We applied it once, applied it twice, applied it 3 times, and applied it 4 times. Why do we always move with just 1 pixel, right? Nobody ever told you to always move with 1 pixel. You are completely free to move as much as you want. So for example, instead of moving with 1 pixel at a time, you can move 3 pixels at a time to save calculations, for example, right? Nobody can tell you not to do this. You can calculate as many times as you want. So this is the goal of using stride. Basically, stride is the jump size of the kernel while sliding through the image. These are 2 hyperparameters that you would have to specify while building your neural network. The final thing is the dimensions of the output, which is how do we calculate the size of the output from the size of the input, given these different hyperparameters, which are the number of padding, the kernel size. So kernel size is just the kernel. What is the kernel? Is just the weights of the logistic regression. Yeah, go ahead.
I have a question.
Go ahead, Mauricio.
Is always a wise product the operation between the filter and the image input?
Can you repeat, please?
Is always a wise product the operation between the filter and the image input?
Yep, always.
And what is the criteria to choose the values of the filter, the numbers?
Can you repeat this question, maybe?
What is the criteria to choose the numbers of the filter? Because in the previous example, you had -1, 0, 0.
Got you. In this case, we will see, we will explore this further once we finish this lecture and go to the part where we speak about the different architectures. And you will see that people have played with these values millions of times and different things work for different scenarios.
Okay, thank you.
You're welcome. Thank you so much. So yeah, this is how the concepts are related with each other. Quickly, I will not go through like explaining this a lot because we do not have time, but it's a very simple formula. So the more stride we have, the more jumps we make, right? The less values we will calculate. So the relationship between the number of output and the stride is in the opposite direction, right? So the bigger the stride, the smaller the output. Now let's go for the number of input. Of course, the bigger the initial image, the bigger the output of the convolution will be. So this will be a positive influence on the output. Another thing is, as we said, the padding. Sorry. The bigger the padding, the bigger the output image is. And this is the reason why we use padding in the start. So the more padding we have, the bigger the output that we will have. And the final thing is the kernel size. So the bigger the kernel size, the smaller the output. So let's take, for example, the case of 5. This is a 5x5 image. And our kernel itself is a 5x5 kernel. So if we apply it on the image, we can only apply it once. Whereas if we apply, let's say, sorry, come on, please, yep. If we apply a 2x2 kernel, we will have much more space for application, meaning the output of this operation will be much bigger. So again, as we said, the kernel size will influence negatively the size of the output. Now, exactly this formulation, why is this one minus this one divided by, all of this can be thought of, you can, I think, simply understand it alone. It will not take you a lot of time to get it, but it's not very important. This is why I'm skipping it. Pooling. Now, the last operation we'll speak about with convolutions is pooling. Pooling is always very common to see with convolutional neural networks, and what it does, it will reduce basically the size of the output, right? So let's take this image. Initial image like this. We apply some convolutions, we get something like this. Imagine now here, this is 1000, right? By 1000, After convolutions, it becomes 800 by 800. It's still too much work for the neural network. So what you can do is you can apply pooling or max pooling. What pooling will do, it will not do any learning. It will just reduce the size to, for example, 400 pixels by 400 pixels by completely ignoring the small values. What does this mean? As we said, the kernels will slide through the image. If they find the thing that they are interested in, they will have, if they do not find the thing that they are looking for, or the concept they are looking for, they will have a 0 activation. If they find it, they will have a positive activation. So max pooling, what it does, it tries to ignore as much of the small activations as possible and focus only on the big activations. How does it do that? Simply, it looks at this region, 3151, and it will only take the biggest maximum value, which is 5. Same thing for this region. Looks at it, the biggest value is 9, ignores all of these, put only 9 in here, and so on and so forth, until we reduce the size of the input image by 3 times, by 4 times, depends on what you specify for the hyperparameters. The goal of this one is to basically allow the neural networks to train faster, to reduce the number of parameters, and to hopefully make the neural network focus only on what is important for the training. I think we could finish this lecture here. The rest of the lecture is about 3D convolutions, and it's completely useless. I don't think we should go through it because I hate it. It's not very useful, to be honest. Yeah, let's just finish this one and go to the next important part. Just to make sure, do you guys have any questions about the current things that we have covered? So first we spoke about...
why do you hate 3D convolution?
Why do I hate it? It's because it's too much computations and it cannot be done in Colab. So usually research on it is pretty source consuming, right? Resource consuming. But they're pretty useful. Yeah, they're pretty useful. I did have a lot of students working on it, but I needed the university to give them a lot of to give them access to lots of servers. And as I remember, they struggled a lot to get that access. Like it took them more than 3 months to get access to the computations. So this is why I just like gave up working on those. But they're still very useful. They're useful for for video classification. If you guys want, we could go through them after we finish the next part, because the next part is more important, I think, for me personally. So what we have done in this current lecture, we spoke about linear regression and the way of mapping one concept into another. We spoke about logistic regression, which is just linear regression for classification and still allows us to do the mapping from one concept to another. We saw perceptrons, which is again, just logistic regression, just another name for logistic regression, allowing us to do this mapping. And then we saw how can we extend this. Instead of doing one mapping, we do multiple mappings. And then we saw instead of doing one mapping at a time, we do multiple mappings at every single step of the road, allowing the neural network to understand much deeper than what it would have otherwise. And then we spoke about convolutional neural networks, and it's a way of applying neurons, but not to the whole input, but only to regions of the input, right? So we take the neuron, we don't apply it to all the previous concepts, but only to specific ones which are related to each other. So if you map it into an image like this, these pixels right here will map to different pixels in this flattened representation. And each one of these will be mapped into a point in our output map. This is the concept map. This is the feature map. Other people would call it activation map. Other people would call it the latent space. It has lots of different names, but the most important part is this is the output of one neuron in convolutional neural networks. And basically we saw things such as stride. We saw things such as padding, and we saw things such as max pooling. Hopefully, do you guys have any questions so far? if there are no questions, then let's go through this beautiful slides. And this is just 7 popular image classification models in ImageNet Challenge. This is the name of the ImageNet Challenge competition history. So ImageNet Challenge is just a beautiful challenge that covers 15 million labeled high resolution images, covering 22,000 categories, right? So it's a very vast data set that took over 25 years to annotate. A very tremendous work. And thanks to this beautiful data set, now all the richness that we have in computer vision came to it. So who created it? This is some information about who created this data set. It was published by Stanford University, and they worked on it for a long time with lots of students, lots of people. Especially, remember, this is at the time where computers were not very fast, and annotation was taking a lot of time. So the popular architectures that have won, the first one was in 2012, sorry. And this architecture, you guys don't see any, yeah. I really have to learn how to do presentations with this one, but yeah. So the first one is AlexNet. AlexNet was the first convolutional neural network to basically participate in this field. And in 2012, it won with a big jump over other models such as SVM, decision trees, boosting stuff, and all of these models. So it was the best model at the time. And sorry. And it is exactly the reason why CNNs are still dominating the field. This is the basic CNN as we have studied it today. And here you will find some information about it. Nobody uses AlexNet anymore, so I don't really want to spend time on it. This is the next one, which is ZFNet. It's just a small extension over AlexNet. And just to go back to your question, Mauricio, again, about the sizes of these windows and all of these concepts. So the only thing that is different between ZFNet and AlexNet is these values, right? So what they did is they experimented with different filter sizes. They experimented with different layers. They just changed a little bit these values in order to give it better results. And that's what really happened. So after they experimented all of these different values, they gave better results. And this is what I'm going to give you. What you should do is always change these hyperparameters as much as you can and see the influence of that on your results. In real life, you're not going to be doing any of that. You will just take one of these models that you look at. They already have the values for these things, and you would just directly train on your data, right? So you will not be spending much time focusing on the values or the sizes of the filters or how many layers in your neural network, because this is something that other people are doing, and they just repeat it millions of times, and they take the best. You just take the best of their best and work with it. The next architecture is something that was pretty interesting, which is GoogleNet or Inception version 1. I think now we have like Inception version 4 and or 5 maybe even, and they have like different stuff. But the main idea that they have added is this idea of one-by-one convolutions. So this is what is it called? Inception version 1 is called also GoogleNet because Google was the one who developed it, and it gave very, very big improvement over the previous one, which was 11% error. Now we are at 6% error, which is like a very big improvement again. And what they have done is that they applied multiple sizes of convolutional filters on the same input. So this allows it to learn again much better representations. And how they did that, how they saved some of the calculations, is by using these one-by-one convolutions. So in order to understand a bit more about one-by-one convolutions, let's come here. So one-by-one convolutions are very useful operations. So this is what a convolution would do. Just one kernel, this is a kernel, takes an image, this is the image, and it would give you one output feature map. So why do we use one-by-one kernels? Like 3x3 kernels, it's pretty useful because it will combine all the information in this region and learn some spatial information, right? So this spatial connectivity between the different points allows these convolutional neural networks to give their best. So why is this unintuitive one-by-one convolution idea works very well? The trick behind it is to reduce computations, right? So what it will do is, usually if you have a very big neural network, the number of filters in one layer would be something like 250, let's say. So if you have 250 neurons in one layer, this means you will have 250 output feature maps. This is a lot of calculations. So what they do is they would take this pixel from the first pixel, for example, from all of these feature maps, let's say these are 250, and find some nonlinear mapping from here to only, let's say, 12 feature maps. So what you just did is you combined these 250 feature maps into something more condensed, which is just 12 feature maps. And then from here, if you apply your 3x3 convolutions, you will save a lot of weights, you will save a lot of training time, you will make it much faster, and you will be able to train for much longer and hopefully get better results. So this was the trick about one-by-one convolutions. You combine all these different channels into the same one, in this case, so this is just one channel, but you could have it like in several, instead of just one, this is just too fast, right? But it's not very good. You could do something like repeat this one, you could repeat this operation into like 12 times. It will be big, but it's not as big as 129. So it's much faster, but still retains as much information as possible. So the usage of this idea of, what is it called? One-by-one convolutions had like many very useful operations, such as dimensionality reduction. So going from 192 to 32. So this is a lot much faster than what you would do with, so this is the goal. So basically apply a 5x5 kernel, but not spend as much resources and computations and time on it as you would have directly. So by applying this one-by-one kernel before, you first reduce the shape, you first reduce the shape of the data, allowing this 5x5 kernel, which will learn these spatial information, to learn from a smaller, more condensed information space and to learn faster. So the goal is not to have a very slow training, but with lots of information, but to have fast training. So with this fast training, you will be able to make more steps in gradient descent, meaning you will be able to learn better. So this was the trick of one-by-one convolutions. Its idea is to basically reduce the size, allowing you to build longer neural networks and make more work with smaller yet accurate models. So here you could find a very beautiful explanation of each one of these applications, but the main one is basically to reduce the size in order to get good results. And this is what they have done here. So they have applied different 3x3, 5x5 kernels, but instead of applying it through the or on the output on the input directly, they apply it after applying these one-by-one convolutions and reduce drastically the time of the training. Sorry. Now the next one, which was the runner-up, is VGG. And the VGG network is something proposed by Oxford University. It's a very beautiful architecture. It's not the best at this time. So this was the best at that time, which in 2014, it was Inception that was the best. But one problem with Inception was that it's pretty slow still. VGG network was a bit runner-up. Still, it was a very slow one, but it gave a very beautiful architecture that is currently still used in things such as style transfer. So usually in style transfer, what we do is we take the output of these layers. And since this architecture is pretty simple, does not have a lot of weird concepts going around, it's very useful to extracting features used for style transfer, as we just said. The next idea that is very useful is ResNet, and I think we should stop here because the rest of them they're not very useful to understand, and we sadly do not have enough time. But yeah, so ResNet is the next idea. ResNet, it's just flexing muscles on the community of computer vision. So this was proposed by Microsoft Research. And what they did was people are training neural networks with 16 layers. Now let's start training neural networks with 250 layers. So 250 layers, this was a crazy number back then, but Microsoft was able to do it. First, because they had the resources, and second, because they introduced a very cool idea that is still being used in different architectures. This idea is called skip connections or residual blocks. So these residual blocks is just a sequence of convolutional layers. So here we have convolutional layer, max pooling, convolutional layer, max pooling, convolutional layer. They put it in a block, but since they have multiples of these blocks, like lots and lots of these blocks, they usually run with lots of problems such as vanishing gradients. What is this vanishing gradients? Remember, when we do the loss function, we calculate its gradients with regards to each layer, and then we calculate the gradients with regards to this layer, but from this layer. So this layer would feed its gradients to the back, and we keep on repeating this operation again and again. Now, if you have hundreds and hundreds of layers, this back propagation of the gradient gets smaller and smaller and smaller and gets less useful and less useful and less useful. So what they said was, we add a small skip connection. This small skip connection is the following. They take the input from here and they add it in here. That's it, just a simple addition. This simple addition in here is able to, then the gradient now passes like this, right? So the gradient passes through here. As we said, the gradient that passes through the whole neural network is very slow and gets very small, but the gradient that passes through these skip connections is very strong, right? It's the same gradient, it's the same intensity of the gradients, allowing the neural network to escape the problem of vanishing gradients and train a very long neural network, even though without fearing any of these problems. So I think, what time is it now? 21:20. So we have 20 more minutes, right? Oh, I see that you guys are sending lots of memes. That's nice. I'm gonna check them out later. That's good. That's good. Keep sending memes, guys. It's very useful. Yeah, so I will stop now and ask you guys, do you have some questions? Any questions?
Will we like go through them deeply, or is this the only time?
If you guys want to go a bit deeper, we can do that. Do you want to go deeper in each one of these architectures?
I mean, it's not a proposal, it's like a question.
It's a question. No, we will not go much deeper. The whole goal of this was to give you a small introduction to, this is the neural network, this is what they added. So usually in computer vision, the increase is very, the change is very incremental. So all of this is just convolutional layers, nothing really interesting. They just added a simple concept of skip connections. That's it. These residual blocks and skip connections, that's it. So this is all you need to understand. It's not really something that you can go in more depth about it, right? Do you guys have any questions so far? Nice. If you do not have any questions, let me ask you a simple question. Do you think you guys can handle a lab right now, or are you just too much, is there just too much information and you cannot really process all of that at the same time?
Depends on the lab.
So the lab is gonna contain as much information. It's very information dense, to be honest. It contains a lot of information too. I think I would rather just give you the rest of the day off. And this is just the introduction lecture. I don't want you guys to be too scared of the course. I hope the course gave a good introduction to, at least this lecture gave a good introduction to those who do not know what is convolutional neural networks. And those who already knew what are convolutional neural networks, at least they benefited from this lecture, right?
Is this lab gonna have like also introduction info, or is it just the next stage?
It's just gonna be how you would train an image classifier in TensorFlow 1, in TensorFlow 2, and in PyTorch.
I think there is a possibility that you're just gonna send it to Moodle and whoever wants to do it.
Okay, let me just quickly go through it. Let me right now just quickly go through it. And if you guys find it too challenging, we repeat it next lecture, okay?
Okay.
Advanced computer vision. Lab 1. I'm gonna send it to you guys on the, no, not this lab. Ooh. This one. No, not this one. Nope. No, this should be. Yep. Looks like it. Or is it not it? Yep. One. Yeah, there it is. PyTorch example. Let me share this. And the link can be viewer. Okay. There it is. So I'm going to share my screen, but on the laptop, because yeah. So just quickly going through this, can you guys still hear me?
Yes.
Yes.
Nice. So the content of this one will be just speaking about ImageNet, pre-trained models, how can we find them in PyTorch, and what is fine-tuning. Then we will speak about how to do it in PyTorch and how to do it in TensorFlow. So here, this is the ImageNet challenge. ImageNet is made from the images of objects from the hierarchy that is provided by WordNet. Yeah, the WordNet. And this is the hierarchy. So for example, mammal, placental, carnivore, canine, dog, working dog, and a husky. For example, vehicle, craft, warcraft, sailing vessel, sailboat, and then we go all the way up to the smallest one, which is trimaran. The winners of this architecture are the following. So as we can see, we started with shallow architectures before convolutional neural networks, and then with convolutional networks, we made a huge jump. This made convolutional neural networks very important. And as you can see, the number of layers has continued to increase until ResNet with 152. And thankfully, with ResNet, we were able to even surpass the human level of error. So now the models are even better than human beings at identifying these classes. PyTorch models, you can find them in the torchvision.models repository, and here are just a list of these models. So here you can find, for example, ResNet 18, AlexNet, SqueezeNet. SqueezeNet is pretty beautiful one. VGG 16.
Isn't SqueezeNet just added the squeeze and excitation block to ResNet?
Yep.
Isn't it? Okay.
Yeah, it's just exactly just what you just described. It's another extension over ResNet that provided two different concepts, which is just squeezing and expansion, and they're both based on one-by-one convolutions. So it's just using one-by-one convolutions in a different manner to provide faster training and better results. We have VGG 16, we have DenseNet, we have Inception version 3, GoogleNet, ShuffleNet, MobileNet, ResNet 50, Wide ResNet 50, and MNASNet. You see there are lots of them, and they're all very ugly. Let's take, for example, the ResNet 18 architecture, and you will see that it just composes from different convolutional layers, different batch normalization. We will speak about it a bit later on. ReLU, max pooling, and here are the different residual blocks, right? So here you'll see convolutions again, ReLU again, convolutions again. You might find some max pooling, beautiful max pooling. Here it is, beautiful max pooling. You already know what that is. I think the only thing that you do not understand here is batch normalization. Batch normalization, a very simple concept. So what you do is you take, for example, the input. Let's say the input was 8,000 and minus 800, right? You normalize the input, and it becomes between -1 and 1. Now, batch normalization is not about normalizing the whole input, but about normalizing the output of convolutions. So the output of convolutions, this is the convolutional layer. Let's say the convolutional layer gave you -5, and here it's 6. So what you will do, you will apply the same trick of normalization, but only on the batch. So these values become between -1 and 1. This is the trick of batch normalization, and usually it gives you more stable training and much better results. Yeah, this is the rest. We will just continue with lots and lots of different convolutional batch normalization ReLU. ReLU is just an activation function for those who don't know it. It's very similar to what you have seen already, such as sigmoid and that, but it's much simpler. So instead of having this kind of non-linearity, which is very difficult and has difficult gradients, we have a simple function, just like this. Either it's the same, x, so this is a linear function x, or it is completely 0. So it's a very simple function. The gradient is very easy to compute because it's just one, and it gives better, faster training. Now let's just move on and start speaking about what fine-tuning is. So fine-tuning comes from transfer learning. Transfer learning is a very huge field, and instead of just spending a lot of time speaking about it and about its different categories, we will just speak about fine-tuning in general. So fine-tuning is just a simple idea. You take a model that was trained on ImageNet, and you fine-tune it to work on your task. So for example, ImageNet detects all types of dogs, all types of cats, all types of patati patata. But for you, you are just interested in building a classifier between, for example, well, let's say salt and cocoa powder. You're just trying to build a classifier between these two. You have a small data set, 200 images of salt, 200 images of cocoa powder. You cannot train a big neural network on that. So instead, you take an already trained model and you train it, or you fine-tune it on your small data set, and it usually gives very good results. This is the good thing about fine-tuning and the good thing about these pre-trained models. To quickly go through this PyTorch example, there are 3 main steps you should take while studying or while building a PyTorch model. Usually in this case, it's a very simple model, so all of them will be simple. The first one is data loading. Second one is model building. Third one is the training. In the first one, there are three main tasks. First is the data source. So the source of the data. The second one, transformations. And the third one is the data loader, or the loading part. In each one of these steps, you will have different, what are they called? Different options, different hyperparameters that you can play with, and different choices to make. So here, for example, this is the data source, and it is a data set that already exists in PyTorch. So it's a very simple one, you call it like this. But if you are working with a specific data set that you are working from your laptop, usually you will have to write the functions of reading the images, of getting how many images in there, associating the images with their classes. You will have to write all of this code manually, or you will find something that is already written and you just change a little bit some of the steps. The second thing is the transformations. For the sake of this beautiful lab, we will have no transformations whatsoever, only converting an image to a tensor and normalizing the input to having 0.5 mean and 0.5 standard deviation. But if you would like to understand what are the different augmentations possible, you can come to Augmentations. It's a beautiful library that gives you the following. No, I want the website. Yep, augmentations.ai. A demo. So here you will find different things that you can apply. For example, here, this is some blurring. You can flip it. So these are the different transformations. These are just used to augment your data set. This is motion blur. Let's see, contrast stuff, RGB shift. Just changes a little bit the values of the RGBs. To grayscale. Crop, just random crops. Downscale. Channel dropout, as you can see, just drops some of the channels. I think there's random brightness. Yeah, you just change the brightness and the contrast, for example, as you can see. Yeah, and just this gives you more samples to train, gives you ability to train better classifiers, right? So here it is. This is what transformations is. You have lots of choices, you have lots of options, especially if you're working on a specific data set or, for example, medical images. There are some transformations that can be applied, some that cannot be applied, so you have to be careful with that. And the last one is the data loader. In our case, it's a data set that already exists, so usually everything is pretty simple. We just specify, do we have a specific order that we need to follow, or we just can shuffle the data around just to make sure that the neural network is getting different batches every time. The number of workers, how many workers are loading the data from the, how many processes are loading the data from the disk. So this one, the higher it is, the faster it is, but the higher the CPU consumption, so be careful. And this is the batch size, is how many images do you afford to take from the disk to the RAM at one specific time. The higher it is, the better, but again, you will have some problems with the RAM. Now let's move forward and go to the next step, which is the building of the classifier. In this case, you have two functions. The first function is the init function, where you define all the layers. In here, you just you define the layers without the logic. So for example, this is convolutional layer 1, convolutional layer 2, max pooling. This is the fully connected layer 1, fully connected layer 2, fully connected layer 3. And in the forward function, you define the logic. This separation of the layers from the logic or the order allows you to build anything you want. So for example, if you want the image to, or if you want here to go multiple times, you say for I in range of 20, and it will go through the same layer 20 times, just for the sake of it, right? Makes no sense to me right now, but maybe for some research purposes, you want to do it. You can do it easily in this formulation. It's pretty simple. Anything you think of can be put in this area. So here you see, we send it through convolutions, send it through ReLU, send it through pooling. Then we put it in this variable X, send it again through all of the list of these operations. Here we are just doing some flattening. So we convert an image into a flat array because we will send it through a fully connected layer. Fully connected layers, they only operate on flat arrays. We send it through flat arrays, send it fully connected layers, send it through ReLU again and again and again, and you have the output. Here you're just sending it through the GPU. I'm sure all of you guys understand how to communicate with the GPU of CUDA. Now the training logic. I will not go through all of this because this is just Python programming. The majority of it is just so to give you these beautiful visualizations, beautiful numbers, beautiful visualizations here. All of this code is pretty useless. Only thing that is important is the following. Creation of the loss, cross entropy loss. Creation of the optimizer, stochastic gradient descent. There are others, such as, for example, Adam. It's also very nice. Now, this is the epochs. Epochs means how many times do you go through the data set completely. And the next one here, now inside it, you are going through different batches in the data. You take the data, split it into labels and inputs or images, send both of them to the GPU, send the input through the neural network, you get the predictions, compute the loss between the predictions and the labels, calculate the gradients with this loss of backwards, and then make a step. This very important separation between the calculation of the gradients and the step allows you to also do anything you want to do. So if you want to currently calculate the gradients and then do some other processing and calculate more gradients and then make a step in that direction, that's possible. If you want to do it directly, that's also possible, right? So this separation is used for researchers to allow them to have all the control they want. Now, why do we do this optimizer.0grad? It's because we give this too much freedom to the user. Maybe the user might make some mistakes, calculate some gradients from here, calculate some gradients from there. To make sure that there is no mistakes, there are no gradients that were pre-calculated and influencing the training, we use this 0grad, and it will just remove any gradients previously calculated, and only the gradients calculated at this step would influence this step. The rest is just Python programming. So here we can see it. Now let's go to the case where we use, we ran out of time. Yep, now let's go to the case where we use pre-trained models. So in this case, we do not use any convolutional layers. We just use a pre-trained model. This is our beautiful pre-trained model, ResNet 18. We just add on top of it a final classification layer with our specific number of classes. So if I had 20 classes in my dataset, we would have 20 here. If I had only 10, we would have 10 in here. And I just replace the final layer of this beautiful architecture, ResNet 18, with an NN layer linear 520 by 10. So if you come here, you see the final layer. This is the layer that is used for the that is used for the calculation of for the classification, and it takes 512 features and converts them into 1,000 classes. In our case, we don't have 1,000 classes. We just have one. We just have 10. So we replace this. We replace this one of what are they called? Sorry, guys, my brain is freezing. So we replace this layer of the neural network that is used for classification of 10,000 classes with this layer that is used only for 10. The rest is exactly the same. We do the training and we find that this model works much better. I will not go through the TensorFlow example, especially for TensorFlow 2, because it's exactly the same logic as PyTorch. So as you can see, the definition of the model, the definition of the logic, the training is also the same. Everything is the same. Whereas for TensorFlow 1, things were much more complicated. So here you define the model and then you add the layers as you go. There's no separation between the layers and the logic. So here you just define the order and you don't have any control over the logic. It's easier if you're doing something not research related, but it's very hard to work with this if you're working for a research task. I'm gonna stop here and thank you guys all for attending. If you guys have any questions, please save them all for the next week, because next week we will have we will go through this again, and I will give you enough time to ask all the questions you want and answer everything you have. Just one small information that I wanted to share with you. Next week I will be in Italy, so I will be with like on a conference, and I might not have a private place to give the lecture. If once I get to Italy, I will have like some maybe hotel room or something where I can give you guys the lecture without being interrupted by people coming in and out. We will have the lecture normally. If I do not, then we will just try to reschedule that lecture on a different day. So thanks a lot, guys. Have a great weekend. Enjoy the time. Sorry if I took some of the more time. And have fun. I hope this lecture was useful, and I hope that you guys will like the course. Thanks a lot.
Thank you. Goodbye.
Thank you and goodbye.
Bye-bye. Have a great day.
Bye, thank you.